Hi there. We're going to look at a heat conduction problem now. Okay. This is going to be one in which we have heat flowing through two substances. Okay. So we've got a 0.75 centimeter thick sheet of aluminum. That's here. Is up against a 0.5 centimeter thick sheet of wood. That's over here. On the aluminum side, the temperature is 8 degrees Celsius, while on the wood side, the temperature is 22 degrees Celsius. And we're going to calculate a couple of things here. We're going to calculate, first of all, the rate at which heat flows through this combination of materials. Actually, the amount of heat per square meter. And then we're going to calculate the temperature at the boundary. In other words, we're going to calculate right here at the boundary of the aluminum and the wood what the temperature is. Okay? Presumably, it's going to be somewhere between 8 degrees Celsius and 22 degrees Celsius, but we'll find out what that is. Okay? So, first off, when we're dealing with heat flowing through a succession of materials like this, okay, then we basically use our heat conduction formula that's got the R values in it. Okay, so in other words, what we're going to say is we're going to start out by saying, okay, Q over the time, the amount of heat per time, is equal to A times, that's the area, times T hot minus T cold divided by, and what we're going to divide by here is the sum of the R values, okay, of all of our materials that the heat has to flow through. And just as a reminder, R here for any material is equal to the thickness divided by the thermal conductivity. Okay? Essentially, the greater the R value, the harder it is for heat to flow. So, in other words, good insulation has a very high R value. Materials that conduct heat very well will have a low R value. Okay? So, first thing we got to do is we got to figure out what R is. So, I'm going to say, okay, R equals L for the aluminum divided by K for the aluminum, plus L for the wood divided by K for the wood. Okay. Let's see. L for the aluminum, this is 0.75 centimeters, so that's going to be 0.0075 meters. K for aluminum is 240 joules per second meter degrees Celsius. So kind of weird units there. Okay. The thickness of the wood, let's see, that's 0.5 centimeters, so 0.005 meters, divided by K for the wood, which is 0.15 joules per second meter degrees Celsius. Okay. One thing to notice here is that K for aluminum is much, much larger than K for wood is. In other words, aluminum conducts heat very, very well. Metals in general do. Okay? We'll see the consequences of that later on. Okay? But anyway, when we add all this together, we get an R value of 0.0334, and that has got the funky units of second meters squared degrees Celsius per joule. Okay? So let's put all this together then and figure out the rate at which heat is flowing through this material. So it's going to be Q over delta T is equal to, now we want to know how much heat, the rate at which heat is flowing per square meter. So I'm going to take A, my area, to be 1 square meter. Okay? And T hot minus T cold, well, it's 22 there, it's 8 there, so the difference is 14. Divided by my R value, which is 0.0334 second meters squared degrees Celsius per joule. Notice how the units are going to work out here. The meters squared are going to cancel, the degrees Celsius are going to cancel. I'm going to be left with joules per second, which, you know, we're calculating energy per time, so, you know, that's what we're expecting. And when we work all this out, we end up with 420 joules per second. Okay? So that is our answer to the first part. That's the rate at which heat flows through the barrier per square meter. Okay? Now for the second, Okay? So now for the second part. All right? Here we want to know what the temperature is at the boundary between the aluminum and the wood. To figure that out, I'm going to take my same principle here, okay, heat conduction, and I'm going to apply it to just the aluminum. Okay? So the idea is if I've got 420 joules per second flowing from left to right through this thing, okay, that's going to apply to both the aluminum and the wood. So if I consider just the aluminum, I can say, okay, Q over delta T is equal to K times A times TH minus TC divided by L. Okay? And I now know that Q over T is 420 joules. So 420 joules is equal to 240 of, whatever those units are, okay, times 1 square meter times TH minus 8 degrees Celsius, right? Because this side is 8, this side's going to be warmer. So the temperature here at the right edge of the aluminum, which is what I want, that's going to be my TH in this, if I'm considering just the aluminum. Divided by L, the thickness is, again, 0.0075 meters. Okay? And notice I know everything in here except TH. So when I solve that for TH, it equals, where's that number? There it is. 8.013 degrees Celsius. Okay? So that is my temperature right there at the boundary. Notice it's almost exactly the same as the other side of the aluminum. Okay? And this is what comes about from the fact that these two K values are so different. All right? So in other words, heat flows very rapidly through the aluminum, but it doesn't flow very well through the wood. And so as far as heat flow is concerned, okay, it's almost as if the aluminum isn't even there. All right? And so that's why the temperature here is basically the same as the temperature there, or very, very close to it. All right? That's it.